There's a bunch of stuff in there. You would have had you should have had about an hour to work on it. Is there anything from what I assigned yesterday that anyone would like me to go over? Yes. Number 6. Let's do number 6. Okay. Number 6 looks like this. It says a body is traveling at 18 meters per second, comes to rest after undergoing a uniform negative acceleration for 40 meters. What is the acceleration on the body, and how long does it take to come to rest? So, based on... Wait, is this the number 6 you want me to do? Yes, that's number 6 you want me to do. There's only one number 6. So you've got an initial velocity of 18 meters per second, and we're told body comes to rest. So that means if you're coming to a rest, that means your final velocity is going to be 0. We don't know what the acceleration is. That's one of the things we're looking for. We do know that the distance that acceleration happens over is 40 meters. So part A wants us to know wants us to find what the acceleration is, and part B wants us to find the time. So that's the scenario there. So we've got 4 kinematic equations that we can use involving acceleration. They are these ones. I'll just write them down here. Vf squared equals Vi squared plus 2AD. Vf equals Vi plus AT. D equals VIT plus 1/2 AT squared. And D equals Vi plus Vf over 2 times T. So these are the ones that we're using. So if we're looking for the acceleration, we've got Vi, Vf, and D. If we're looking for A, this is the one that we're going to have to use for that one. So we've got Vf squared equals Vi squared plus 2AD, and we can fill the thing in. Vf equals 0, Vi equals 18, and we're squaring it. Plus 2 times A is what we're looking for, and D is 40 meters. So before I start to isolate for A, I can just clean this up a little bit. 0 is going to equal 18 squared is 20 squared is 200. 19 squared is 18 squared is 324. Yeah? Yeah. Plus 80A. So I'm going to subtract 324 on both sides. 324, so I'm going to get negative 324 equals 80A, divide by 80, divide by 80. And we should get something in the neighborhood of 4 and a bit. Negative 4 and a bit. Which is one of the options down on the bottom of the page there. Negative 4.05 meters per second squared equals A is one of the options down there on the bottom of the page on the answer key. And then if we're looking for the time, what we would like to ideally do is use information that we have not calculated so we don't introduce any weird rounding bits. So using this same information, find time. If this is the information we're going to use to find T, this is the equation that we're going to use. So we're going to use D equals Vi plus Vf over 2 times T. D is 40. Vi is 18 plus 0 over 2 times T. So that's going to be 40 equals 18 plus 0 is 0, or is 18. 18 divided by 2 is 9. Divide by 9, divide by 9. And we're going to get T is equal to 4 and a bit seconds, which is an option. 4.44 seconds. That's a 9, not an A. Riri, does that make sense? Okay, you figured out where you were stuck? Yeah. Comments, questions, concerns on anything else I assigned for? There was a bunch. I think there was like 14 or 15 questions that I wanted you to play with. Yeah, Brad. The first 5 or the second 5? Can the plane land? Or the Jamaican bobsled? Okay. Let's take a look at 5. The first 5. 5 says a jet plane lands with a velocity of 115 meters per second and can accelerate at a maximum rate of negative 5.25 meters per second squared as it comes to rest. So this is the first number 5. So if a plane's landing, obviously the plane is moving when it hits the ground. So it's got an initial, most planes do, not all, but most. It's got an initial velocity when it hits the ground, when wheels are on the ground, of 115 meters per second squared. And once the plane hits the ground, in a perfect world, the thing comes to a stop before it runs out of runway. And that's actually what we're trying to figure out. Can this particular jet plane land on a small tropical runway airport where the runway is only 0.950 kilometers long? So not every plane can land on every runway. So let's figure out if this plane will survive or if it goes into the jungle. That's an initial velocity. The plane wants to come to a stop on the ground, and it can accelerate at a maximum rate of negative 5.25 meters per second squared. We're using all the ways that planes can brake. We want to know, or we know that this is that value. And if the plane says, sorry, you're good with part A, Brad? Okay. So part B says, can this plane land on a small tropical runway airport where the runway is 0.95 kilometers long? So we're given a maximum displacement, and we want to know if our plane will land within it or outside it. And so what the language there is asking us to find is, what is the actual displacement? And then we're going to compare the actual displacement with the length of the runway. So using this information to find D, we've got VF equals VI plus 2, or VF squared rather, equals VI squared plus 2AD. VF is 0, VI squared is 115. We want to square that, plus 2 times negative 5.25 D. So 115 squared, where's my calculator? 5 squared, boom, that is 13,225. So 0 equals 13,225 minus 10.5 D. I just multiplied these two things together. Positive 2 times negative 5 1/4 is going to be negative 10 1/2. So then I'm going to subtract the 13,225 over onto both sides. So I'm going to get negative 13,225 is equal to negative 10.5 D. Divide both sides by negative 10.5. And we're going to find that given this information, an initial velocity of 115 meters per second, a goal of stopping, and this maximum acceleration, the plane is going to be displaced 1,259.5 meters while it comes to a stop. The runway is only 0.950 kilometers, so that's 950 meters. Is the plane going to make it? Nope. They're either ending up in the jungle or in the ocean if they try to land on that little island. The answer is no. The runway is too short. So this is one of those ones, they give you a displacement, but you have to think about what the question's asking you to do. You're not going to use the 0.950. You need to find out what the displacement's actually going to be and then just compare it to the 950. The 950 is smaller than the minimum displacement required. The plane will not make it. Brad, does that make sense? Yeah. Any other questions from the homework I assigned? Comments, questions, concerns? There was a lot I wanted you to do. Yeah, there was a lot I wanted you to do. But you should have had a bunch of class time yesterday to do it. Nobody wants me to take a look at any of these ones on this side. He showed you this one, yeah? These ones? Okay. No one has any questions about the bonuses? Okay. There's no issues. I could give you a quiz today and y'all would be good. I'm not going to, but I could. Is that what I'm hearing? Mary says no. So are there questions or you just didn't practice at all? Okay, but did he communicate that that was part of what I wanted you guys to do? Okay, because that's a big issue with my TOCs is that they just don't tell my students what I want them to do. Okay. There is no quiz today. I'm not going to give you a quiz today. Did he showed you guys the answers to the back page? It says, please show them these. And it said on my notes, please also show them the answer key and have a copy down for the second page of the assigned work. These are the answers that if you attempt the back page, you need to know. Those are all of the answers, so I didn't assign all of the questions. But copy those down just like you would have, just like I provide them on the previous page. Yes, Yuli. Yes, I will do the super bonus question. Everyone take a look at, while you copy these or take a picture of it. 7 meters, 20 seconds, 0.638 meters per second squared. 6 meters per second squared, 2 million. Is that right? That can't be right. Nope, it's not right. My apologies. I added one more zero. 200,000 is what that should have been, not 2 million meters per second squared. And yes, there was only one yes, no question on there, so that one should be a dead giveaway.
Question 2, it says 21 meters per second, 7 seconds, and then it says the object after 2 seconds. So it kind of like messes with the starts from rest part because we're talking about after 2 seconds, right? So I can't write 0 for VI, I kind of got lost.
Okay. Yuli, can I do number 2 before I do the super bonus? Okay. Here we go. Number 2. So, here's number 2 on the back page. A car starts from rest and accelerates uniformly to reach a speed of 21 meters per second in 7 seconds. What was the speed of the object after 2 seconds? So, Brad, the way you're thinking about it is you're saying VI is our unknown. So don't write down what I'm about to write down. This is Brad's thoughts. So what you're telling me, Brad, is that your VI at 2 seconds is unknown. That's true. Your VF, you're saying, is 21. What other information did you use to try and tackle this question? What did you call your time then? Everything I'm hearing you saying is you are so close to exactly what you should have done. So you have really good ideas. So initially you said if you should use 7 seconds, but you said you should use 5 seconds. If this is how you want to set it up, if you're looking for VI at the 2 second mark, you absolutely need to call that 5 seconds because the entire time is 7 seconds. And if you want to say VI at 2, if you're calling VI the 2 second time, then you're ignoring the first 2 seconds of travel. That would be the absolute correct setup. It's great. The only problem is if this is how you're going to do it, you don't have enough information. You need because you need 3 pieces of information to find a fourth. And so you don't have A and you don't have D. So that's, part of the problem here. What we could do, though, what we do know is that if you consider the beginning, like what you said there at the end, what you said there at the end, if you say, I want the initial velocity to be 0, because then we have a meaningful piece of information, and we know the final velocity is 21, and we know the time is 7 seconds, we can use this information to find A, and then we can actually go back and do what you suggested originally. Once we have A, we can go back and actually do what you suggested here. So if I use this to find A, we know that A VF is equal to VI plus AT, or we could just use the definition for acceleration. We know that when I first introduced the idea of acceleration is the change in velocity over the change in time. So the acceleration is going to be VF minus VI over T. And if we plug this thing in here, VF is 21. VI is if we're starting from rest, VI is 0. And the time is 7 seconds to do that. So then 21 minus 0 is 21. 21 divided by 7 is 3. So then the acceleration of the car is, or was it a car? Yes, it's a car, is 3 meters per second squared. And then you can hop over here. You can do it the way you were suggesting here. If I want VI at 2 seconds, VF is 21. Or you could do it for the beginning chunk. You could say VI is equal to 0. VF is at 2 seconds. So then my time is equal to 2 seconds. My acceleration is still 3. So you can set it up either way, Brad. It doesn't really matter which one you do. I would argue the second one is easier only because you can set VI to 0. Like the physics is identical, but the math is easy. Anywhere where you can set a variable equal to 0, you're less likely to screw up the algebra.
Wait, so in the first 2 seconds, we reach 21 meters per second, like at 7 seconds.
Yeah.
But if we're doing the first 2 seconds, okay, I'll let that as a question.
One of the assumptions that we have to make here, and it's actually a really reasonable one, is that accelerations are constant over a particular problem. If acceleration is not constant, you guys can't do it. And again, that's not a slight against you. If the acceleration is not constant, I've never seen that. Like that would be, that's advanced beyond even my education. That's very specific kind of engineering, the world of engineering, which I don't have any experience with. So with all of these, we're assuming A is constant throughout. If it's not, the only way I know how to tackle it is graphically, which I haven't shown you yet. And so with this assumption, you can tackle the rest of it either way. It doesn't matter. I can show you that they're the same. If we do it your way, I'll write that down here. Then VI is going to be at 2 seconds. We don't know it. VF is going to be equal to still 21. The acceleration is equal to 3. And then your time is 5 seconds. Sorry, I'm off the page. So VF is going to equal VI plus AT. So 21 is going to equal VI, which is what you're looking for if you set it up your way, plus 3 times 5. So it's going to be 21 equals, am I off the page again? I am off the page. 21 equals VI plus 15 minus 15 on both sides, and you're going to see that VI is equal to 6. But you said, and this is your VI that you set to be at 2 seconds. You're looking at the last 5 seconds of the problem. If we do it my way and say, well, I want my initial velocity to be 0, and then I'm going to look at it after 2 seconds, then VF is going to equal VI plus AT. VF is what we're looking for. VI is 0. So it's going to be 2 times 3, which is 6. So the answer is 6. And it doesn't matter which way you tackle it. You can call it the 2 second mark your initial velocity for the last chunk of the problem, or you can call it 2 seconds the final velocity of the first chunk of the problem. Either way, you need the entire problem to find A, and then you can find whatever you want. Yuli wanted the super bonus. Let's take a look at the super bonus. Well, the super bonus is attached to the original bonus, and the original bonus says a driver of a car going 90 kilometers per hour suddenly sees the lights of a barrier. Yes. the lights of a barrier 40 meters ahead. It takes the driver 0.75 seconds before he applies the brakes. This is the reaction time. Once he does begin to brake, he decelerates at a rate of 10 meters per second squared. Does he hit the barrier? And your answer to that problem is yes. There is only one yes, no problem, and I gave you the answer. Yes. Buddy is going to hit the barrier. And at 90 kilometers per hour, it's probably not going to go well. But airbags and seatbelts can do a lot of good, so who knows? Driver's hitting the barrier regardless. Question is, what would the maximum speed at which the car could travel and not hit the barrier 40 meters ahead? So you've got a setup that's going to look like this. This one, for the sake of picturing it, I'm going to draw it. Not well, but I'm going to draw it. There's a car, there's our barrier. Buddy's going this way with some velocity v. Now there is a chunk of time and distance where he has not slowed down at all yet. And so this portion of the problem is a constant velocity sort of problem. We've got Buddy traveling at v. The time it takes for him to stop is 0.75 seconds, or sorry, to start to brake is 0.75 seconds. And during that 0.75 seconds, he's going to travel some distance. We don't know what it is. I'm going to call V max. Because that's, for the bigger part of the problem, that's what we're looking for. For now, I'm going to call this little distance here X. This is an unknown distance that he's going to travel before he even begins to brake. And then once he begins to brake, you have, this is the acceleration portion. Acceleration. And what you want is the maximum velocity that he could be traveling so that at this point, when he starts to brake, he comes to a stop. It's those classic kind of cartoon or movie where he's like, he slams on the brakes and comes skidding to a stop and just like his car barely kisses the wall. So here you've got a VI equals 0. Your initial velocity for the accelerating part, sorry, a VF is equal to 0. Your initial velocity for the accelerating part is going to be Vmax. The acceleration is the same as it was in the original part. Once he does begin to brake, he decelerates at a rate of 10 meters per second squared. So that means the acceleration in here is going to be, and decelerates is an important word. If the deceleration is 10, then the value we're putting here for A is not 10, it's negative 10. Because the unspoken assumption is that car moving forward has a positive velocity. So if you're decelerating, acceleration is going to be negative. So it's going to be negative 10. And we do actually know what this little piece of distance is here. Because the total distance is what? 40. This total distance here is 40 meters. And so if I call this little bit here of unknown distance covered while looking at and realizing he needs to brake, if I call that X, then this stopping, like the actual skidding portion, is going to be 40 meters minus X, this unknown piece here. And so now we've got two portions of the problem. And I can separate this thing up. We know that given VI, VF, A, and D, VF equals VI plus 2, or sorry, VF squared equals VI squared plus 2AD. We know VF is 0. VI is this Vmax we don't know, plus 2 times negative 10 times 40 minus X. And this distance here is X. And now we've got two unknowns here. We can use this information over here to relate Vmax and X to each other, substitute that in over here, isolate and solve. So what I'm going to do is, because I'm looking for Vmax, and that should be squared, because I'm looking for Vmax, what I'm going to do is I'm going to solve this guy for x and then substitute it over here. So we've got v equals d over t that we can look at here. But I don't want that. Well, sure, let's use it. Vmax is equal to x divided by 0.75. So if I want to get x by itself to make this doable, I'm going to multiply both sides by 0.75. That's going to cancel, and I get x is going to be equal to 0.75 Vmax. And so that can be shoved in there. So we're going to get a final velocity of 0 is going to equal Vmax squared minus 20, I'm multiplying the 2 and the negative 10 together, times 40 minus 0.75 Vmax. I'm going to distribute that in, and we're going to get a quadratic, which, if I'm not mistaken, you do learn to solve in pre-calc 10. Or is it 11? You learn how to factor in 10, but the quadratic formula doesn't show up until 11, doesn't it? Okay. So 0 is equal to Vmax squared minus 80 plus 15 Vmax. And then usually that's the thing you have to solve. You're going to get two velocities, a positive one and a negative one. The negative one doesn't make sense because that means the car is going backwards away from the barrier. This thing might actually be, is that easy to solve? I need two numbers that multiply to 80 and add to 15. No, that's not clean and easy to solve. If you did Math 10, either foundations or pre-calc in semester 1, you can solve that. If you haven't seen it yet, if you're in it right now, you will be able to solve it in a couple weeks. Yeah, right now. Your calculator is correct. Because 2 times 40 is 80. 20 times 40 is 800. You are right. Either way, at this point, well, that's worse. I will tell you what the solutions are. X squared minus 800 plus 15x equals 0. Your solutions are negative 36.76 or positive 21.76. So the negative velocity doesn't make sense. If you solve this thing, this one I did not give you the answer for, 21.76 seconds. So that is the absolute fastest, the meters per second. That is the absolute fastest Buddy can go and be able to brake just touching the wall. That 90 kilometers per hour is 90 divided by 3.6 is 25 meters per second is what he's doing in part A. It's a fun question to play with. It is, just so you're aware, well beyond what I would expect you. As soon as I introduce these quadratics, knowing a whole bunch of you haven't taken Math 10 yet or are in it right now, Math 11, or in it right now, this I would not expect you to be able to do a question like this on a test or anything, but it's certainly worth playing with. It's like the absolute kind of grossest thing I could give you, and that's not the kind of thing I'm going to throw in a chapter test. But in your homework, it's good, I think, for you at least to see it and think about it. Yuli, does that make sense? Did you get this one? Did you figure this one out? You do? Okay. You're sure you made the mistake and not me? Because I've already made a few this morning. Okay. I mean, there's a reason it's called super bonus. It is, again, well beyond anything I wouldn't give this to a physics 12 class. It's still beyond even what I would expect them to produce on a test. But it is the kinds of concepts that we're looking at here already. So, are there anything else from the homework anyone would like me to go over before we move on to graphing accelerations? Okay, if there's nothing, then a few more people snuck in while I was going over yesterday's work. If you haven't done this stuff, I would, like, whether you didn't get it done yesterday or you were away yesterday or whatever, I would strongly encourage you to go back and take a look at these things. These 4 kinematic equations are foundational to the rest of our semester, to a huge chunk of what you'll look at in grade 12. They do kind of just show up here, and we're talking about accelerations, but the closer we get to being able to actually approximate real life, the more likely those things are going to be coming up again and again and again. This is a really important concept to be able to be comfortable with. Use the time. Come see me at lunch if you need it or whatever. Emma, a fictional character you'd like to spend the day with, you're guaranteed to survive. The Joker. Kale. Captain America. David. Fictional character you'd like to spend the day with, you're guaranteed to survive. Okay. So I'm still missing Grushan, Jack, Manette, Rain. Oh no, Reyna. Same question. Thanos? Venom. That would be way more entertaining. Kaylin, Harleen, and Jaden are still away. Okay, cool. Venom. That would be a fun day. Kind of a gross, barbaric sort of day, but. Sorry, who? I don't think so. See, the beauty, though, is Venom and Eddie are still there. You'd be witnessing the psychotic break of Eddie Brock. So the idea with Venom's a really interesting one, because Venom is, like, the whole premise there is that he's an alien symbiote, so he requires another organism to be able to survive. So he's bound together with Eddie Brock, but over the course of just the day-to-day, it's just Eddie Brock talking to Venom kind of within himself. But he verbalizes. It's not a subconscious. It's a verbal thing that they're talking back and forth. And Venom isn't actually, like, he doesn't start as a superhero. Eddie Brock is just friends with a convenience store clerk who's getting robbed, and he quite likes her, and so he eats the bad guy. Venom also needs to eat. So, yeah, that's one strategy. Venom's awesome. Venom's fantastic. Super dark, but pretty awesome. Venom's big bad guy is the first. Carnage was the first cartoon character to ever give me full-blown cold sweats nightmares. It was awesome. Me, as a child. I saw Carnage for the first time, the guy Venom's big bad, and full-blown nightmares for a long time. It was awesome. Dwayne. Yes, do what you got to do. Okay, here we go. We're going to graph. Everything we do, we're like, here's the math, now let's graph. Here's the math, now let's graph. We looked at constant displacement, and how you displace. If you displace over a time, that relates to a velocity. If you do that constantly, there's a relationship there. If you start to accelerate, the graph's going to look a particular way. And now we're going to bring in this idea of, well, what if I have velocities and they're changing over a period of time, and I graph those? What kind of information can we pull out of that? And those are actually really quite useful tools to look at. So we'll see how far we get in the next half hour. Review, just a wee bit of review. I would not say that Venom is a well-made movie, but the cartoon version of Spider-Man from the early 90s that I grew up with, fantastic, and that's what gave me nightmares. Okay, will do. So, review. If we recall, when we graphed D and T, a displacement graph, and how you name this thing, it's the same concept. We name it three different ways. It's either a displacement graph or versus time graph, a position versus time graph, a distance versus time graph if the thing never goes negative and then you're looking for speeds. A displacement time graph or position time graph looks like this. Let's just talk about one here for a second. I got a straight diagonal line, a straight flat line, and then kind of a curved line. And we're going to put all of the pieces that we looked at on this graph. If you recall, if we wanted to find a either position or displacement on a graph like this, all you had to do was read the axes at whatever time you were concerned about. That would give you position. If you wanted to look at displacement, you're just comparing two different times on the graph. You'd say, okay, well, he was here, he is now over here. This difference is displacement. Shoot, didn't give myself enough space. The difference here is displacement. Either one of these locations is a particular position. At a given time, he's there. At another given time, he's there. The difference between those two is displacement. And then if we said if we take a look at a position or a displacement, or if we look at a displacement and we divide it by the amount of time, so right here, that's that time. Over here, that's that time. If we compare the displacement to the amount of time taken to displace, this is our time interval. So if we take our displacement, we divide it by our time, we found velocity. And so for individual chunks of the graph, if velocity is equal to a change in position over time or a displacement over time, for different chunks of the graph, this was related to what graphical concept that you learned about in grade 10 or grade 11 for some of you. Displacement is on the y-axis, time is on the x-axis. If I look at a changing in the y-axis divided by a changing in the x-axis, what concept is that? A change in y over a change in x is equal to a rise, how far are you moving vertically, divided by a run, how far are you moving horizontally. To find velocity on a graph like this, what do we find? What are we using? The slope. We looked at that a couple days ago. The idea that if I give you a position time graph, or displacement time graph, whatever I call it, slopes are going to give you velocities for different chunks of the graph. So this one, this chunk of the graph, has a positive slope. So I know here, and it's constant, it's a positive constant slope. So what this means is if the slope is constant, the velocity is constant, and if it's moving up and to the right, I know my velocity is positive. So I have an object moving at a constant velocity in the positive direction, whatever I called that previously. For this chunk here, if my graph is flat, you can think of that two different ways. The one way is to say, okay, well, my graph is flat. Flat lines have no slope because they have no rise. So then if the slope is 0, my velocity must be 0. Or to think about it in a purely physical way, my position hasn't changed. And so if your position hasn't changed, it means you're not moving. Like all of you right now are sitting in your desk, and you've been sitting in your desk for the better part of almost an hour. You haven't gone anywhere, therefore you can't be moving anywhere. So your velocity is 0. Again, in a physical sense, it makes sense. In a math kind of slopey way, I'm hoping it makes sense. And then when I gave you curved lines on position time graphs, for something like this, we had a slope that was increasing, i.e. the line is getting steeper, And if the slope is increasing and slope is velocity, that means velocity is increasing. And if your velocity is increasing, that means you must be accelerating. And at this stage, we had no way of saying what the acceleration was. We just know that the object is speeding up. I gave you one other exercise we went through when I gave you curved lines on position time graphs, is to say not only I can say that the object's accelerating, we can actually find what the acceleration at a particular time is. We can look at this idea of, sorry, not what the acceleration is, but what the velocity is while the thing's accelerating. So for example, at that time right there, if I wanted to know instantaneous v, instantaneous velocity, at that point right there, we drew what I introduced to you as a tangent line, which some of us took issue with, and that's okay. It was your first time being exposed to it. I think I only gave you 4 or 5 of them to play with. If I wanted to find instantaneous v, we're using a tangent line and finding the slope of this. And then when I gave you the practice for it, the picture was relatively small. It wasn't a super easy one to do. I gave you the answers that I came up with. Not a lot of you asked me about it. But I'm going to get you guys doing a bunch more practice with it in this section. Questions, comments, concerns about any part of what I'm calling review, something we looked at last week. Okay, so we're going to take the same set of skills and we're going to apply it to a different kind of graph. We're going to look at a velocity time graph now. Given a velocity time graph, instead of a position time graph, given a velocity time graph, we can find, just like on a position time graph, reading things off the axis gave us positions and times. On a velocity time graph, if I wanted to find the velocity, you can just read it off the y-axis for a given time. The data on the graph, the way the thing is labeled, will tell you specific things. So if I go down here and I look at this graph down here, and this is a velocity time graph. You look at the labels on the sides, I've got velocity there, I've got time there. Positive is meters per second north. If I wanted to find a bunch of velocities now, I just read the thing. So if I wanted to find the velocity at 2 seconds, I go over here to 2 seconds. This is one axis. Just so we're really clear, this is 0. This is 0v. That is the horizontal axis. Not the bottom of the picture, but actually that line right there. So if I wanted to figure out what the velocity at 2 seconds was, we go to 2 seconds, we go up to the line. How fast is the object moving at the 2 second mark? Raina, you may. First, you have to tell me how fast the object is going in 2 seconds. You just read it off the graph. 2 seconds, up to the line, over. 30, go to the washroom. 30 meters per second north. Sorry, Brad? Yep. At 6 seconds, how fast is our object going? We go over to 6, and we go to wherever the line is. In this case, the line is down. And we read, how fast is the object moving at the 6 second mark? -10 meters per second. Or another way to write -10, if north is positive, we could say what? 10 meters per second south. Which means at some point between the 2 second mark and the 6 second mark, what had to happen? Sorry? They had to slow down, stop, and turn around. Because positive means you're moving north, negative means you're moving south. If you were going north, now you're going south. At some point, not only did you slow down, you came to a full stop and are turned the other way. That had to have happened here. There's no other way to do that. Velocity on a velocity time graph is just reading it off the graph. When you're ready, flip the page. Things get more interesting. There's the graph there again. When we were looking at position displacement graphs, position and displacement versus time graphs, the next thing we looked at, we read things right off the graph, and then the next concept that we looked at was, well, what does the slope represent? And on a position time graph, if you look at a rise over a run on a position time graph, a rise is a change in a position, a run is a time, so displacement divided by time is velocity. How quickly you're moving, changing your position, is velocity. So the next thing that we're going to look at here is, well, what does the slope mean? This section of the graph is a flat line. So if I asked you for the slope of a flat line, the slope here is equal to what? Flat lines have a slope of 0. And so then let's tie this idea to what's actually happening here. On this portion of the graph, from 0 seconds to 3 seconds, our object has a velocity of 30 meters per second north the entire time. So if the slope is 0 on a velocity time graph, that's equivalent to saying, well, we have a constant velocity. And we can read whatever that velocity is here off the side. 0 slope is constant v. So then what happens if I now have a non-constant slope? Sorry, a non-zero constant slope. The slope here is not 0. What's the slope here? Without calculating it, if it's moving down to the right, the slope is negative. It's not 0 anymore. I have some negative number here. And if we look at physically what's happening here, I have a velocity, this is what Ray Reed said before, when I asked the question, what has to happen if I was at 30, now I'm at negative 10? We have to slow down. So this portion of the graph up to this point here represents slowing down. At that point right there, what's our velocity? 0. So what happens at that point right there? You've stopped, and then the line continues. The slope is the same as it was before. Here we were slowing down. Here we've stopped. What happens for this little chunk of time? We turned around and we're speeding up backwards, or in this case, south. So then what does the slope on a velocity time graph represent? It represents you're slowing down and you're speeding up the other way. That concept we called acceleration the other day. So we can find, so I'll go this way, slope on a VT graph, velocity time graph, is equal to your acceleration. And if you recall, slope was a rise over a run. If I look at what concepts are rising and running here, rise is how is my velocity changing? The run is how is my time changing? Change in velocity over change in time, we defined to be acceleration a couple days ago. So if I give you a velocity time graph, if I ask you to find acceleration, what you're looking for is the slope for a chunk of time. So let's go ahead and do that. I want to make a couple notes in here about some of the stuff that we just said. This chunk of the graph right here, we said was slowing down. There's a couple people who said that. They were right. Why is that slowing down? Well, it's slowing down because if you think back to how we talked about accelerations on the very first day for acceleration, we have a positive velocity that's going down towards 0. So I've got a positive v and I've got a negative a. For this chunk right here, we're slowing down. At this moment right here, we've stopped because velocity is equal to 0 at that point. But the stopping point is also where the object turns around. The only reason that we hit 0 velocity is because our object is slowing down to a stop and then immediately starts speeding up the other way, which is this chunk right here. For this little purple chunk here, I've got a negative velocity. We've dropped below the x-axis on a velocity time graph. And I've still got that same negative a. The slope is still negative. The slope is constant. If my acceleration and my velocity are both negative, it means we're speeding up backwards, or in this case, south. This just speeds up. We're tying it to all the stuff that we looked at a couple days ago. So what we can do is we can find what these accelerations are given the velocity time graph just by finding the slope. If I wanted to find out what the acceleration was from 3 seconds to 4 seconds, so for this window of time right here, the entire time acceleration is constant, I can figure out what that is. Acceleration then is going to equal the slope for that portion of the graph. So that's going to be the rise over the run. Well, rise over run is just a change in velocity over the change in time. What is the change in velocity between 3 seconds and 4 seconds? Well, change in velocity is just v final minus v initial divided by the change in time is just going to be t final minus t initial. If we're concerned about what's happening in just this window here, what is the initial velocity for this chunk of time? It's 30. At 3 seconds, we're up here at 30. The final velocity is? At 4 seconds, the final velocity is negative 10. So if I'm going to plug this into this calculation down here, final velocity is negative 10 minus our initial velocity of 30 divided by our final time is 4 minus our initial time of 3. Negative 10 minus 30 is negative 40. 4 minus 3 is 1. So then the acceleration for this chunk of time is going to be negative 40 meters per second squared, which is a massive acceleration. For those of you who were talking about G's on the very first day when I introduced acceleration, this is about 4.5 G's. For those of you who understand the concept of G's. If you don't, we'll talk about it in a couple days. But just to give you a concept, that's what we're looking at here. Okay, from 4 seconds to 7 seconds, that's this window here. What's the acceleration from 4 seconds to 7 seconds? Without doing any calculations, you can look and say, okay, well, the acceleration here has to be what? 0. Okay, how do you know? There's 2 ways to think about it. There's no rise, or physically, the other way to think about it is what? That's this same thing. You're still using slope there. No rise divided by a 3-second run. But if I want to ignore the math for a second, I want to look just at physically what's happening. Careful, it is moving. This is a velocity time graph. The velocity is staying at negative 10. So now we're not talking about displacement time graphs anymore. On a displacement time graph, this looks like not moving. On a velocity time graph, this looks like constant velocity. This is constant v, not constant d. Constant v means the velocity isn't changing. That's another way to think about what it means to be not accelerating. Constant v is you are moving here because your constant velocity isn't 0. And then if we wanted to figure out what the average acceleration was from 0 to 4 seconds, we know that from 0 to 4 seconds, a bunch of stuff is happening. Buddy drove at a constant rate and then began to slow down. So there's a few things happening in here. We had no acceleration and then we had -40. What we could do though for the same window of time is to say, well, what is the average acceleration? If I wanted the average acceleration, we would do the same thing. We'd still look at a change in velocity over a change in time. And we'd say, okay, at 0 seconds, our initial velocity was 30. At 4 seconds, our final velocity was -10. So we'd have a v final minus v initial over t final minus t initial. And we'd say, okay, well, our final velocity is -10. Our initial velocity is -30. The time final now is 4 seconds. My time initial is 0 seconds. And so this would be -10 minus 30 is -40 divided by 4. We would say the average acceleration is -10 meters per second squared over this entire time interval. Even though we know, based on the graph, that's not what the object did. This one right here is not a super useful concept to talk about. All it says is we would have, what this means down here is that we would have had the same result that we got if instead of accelerating at -40 for a short window, we'd extended that acceleration to -10 over the entire 4 seconds. So there are some applications here, but we'll talk about them in the next chapter. Yeah, man. Yeah, do that. On a position time, questions about this so far? That's first period on a Wednesday. We're all tired. How do we feel about this stuff? Are we doing okay? Sire, you doing okay over there? Colden, are you awake? Okay. Are we doing okay? Colden, are we okay? Okay. The last piece we can look at is this idea then of instantaneous acceleration, tying that to what we looked at before. If I want to know what the acceleration is at a moment in time, we would do it the exact same way we did before. We'd have a curved line on a velocity time graph, and we could find the instantaneous acceleration. Instantaneous acceleration by using a tangent line on a velocity time graph. What would a curved line like this on a velocity time graph represent? We had a straight line representing a constant acceleration. So a curved line is going to equal what kind of idea? If the slope is getting steeper on a velocity time graph, that means the acceleration is? Yes, it's increasing. So a curved line like this is going to represent increasing acceleration. And Kale said it's positive. It is positive. That slope is up to the right. But if I have an increasing acceleration that's positive and a negative velocity, or a velocity that's going towards 0, all this means is you are you're slowing down progressively faster. as you approach 0. So for a window of time like this, what's happening here is you're slowing down faster. This is, I'll make a note down here, while it's something that we can find, this is likely to never happen. Because even though it makes sense mathematically, it doesn't mean we need to do it. This is, I've never looked at this, a changing acceleration. I did my bachelor's degree in physics, my master's in math. I've never seen this. This is an engineering concept. And it has a name. A changing position we call the velocity. A changing velocity we call an acceleration. A changing acceleration we actually call jerk. So if your acceleration is changing, that concept is called the jerk. You can find what is the jerk here. And there will be a numerical value. It'll be a meter per second cubed or a meter per second squared per second. Again, a concept I've never looked at. Engineers care about this. Specific kinds of engineers care about this. I've never seen it. Still something that we could do though. Flip the page. So, velocity time graphs. You can find velocity by reading it off the axis. You can find the acceleration by finding the slope. And on a position time graph, that's all we did. But on a velocity time graph, there's one more piece of information that we can do. You guys have been a great audience so far. We can actually go ahead and find displacement. We can find the displacement on a velocity time graph. You're like, well, how the heck could we possibly do that? How did we find displacements before? When I introduced to you the concept, well, actually, it wasn't part of introduction. How did we find displacement before? Close. V times t. If you're not accelerating, d equals v times t for no acceleration. Okay, well, that's really interesting. Let's tie that to what we're looking at here. If I said to you that your velocity was 20 meters per second, and you did that for 5 seconds, you would say, okay, well, if I wanted to find the displacement, d would be, actually, I'll do that down here, because that's the first one I'm looking at down here. If I said, well, your velocity was 20 meters per second north, the time it took was 5 seconds, and I wanted to know what the displacement was, you would say, okay, well, d is equal to v times t, so v is 20, t is 5, 20 times 5 is 100 meters per second north. And without looking at a graph, this is what you do. It would be nice and easy, no problems. But that we can actually relate to the graph that I've got on the page here. Look at what's happening. I've got on this graph, this is a graph that represents 20 meters per second for 5 seconds. If I look at my graph here, I'm going to highlight the axes just to make them really clear what we're comparing. There's one axis. This is the other axis. That's our time axis. This is our velocity axis. 20 meters per second for 5 seconds represents this portion of the graph here. I'll color that in a little bit more aggressively so that it shows up better on the screen. What shape is that? It's a rectangle. Area of a rectangle is what? What's the formula for the area of a rectangle? Think back to grade 8. Length times width, yeah. If I look at this rectangle, there's your length. Here's your width. if area is equal to length times width, the length of this rectangle is, if we use the axes, the length of the rectangle is 5. The width of the rectangle is this gap here. That's 20. The area is equal to the length times the width. That's 5 times 20 is 100. By finding the area of that shape, what have we just done? That's the exact same calculation I did down here. And so what that means is, there's a really convenient way, if I give you the picture, there's a really convenient way to find yet another concept. If I wanted to find displacement on a velocity time graph, all we have to do is calculate the area under the curve. If I calculate the area, I know how far the object has gone while it's moved at a particular velocity for however long time we care about. When we talk about this concept of under the line, it's important to recognize what that means. So I want to make a note down here. If I want the area under the line, what I'm looking for is the area between the x-axis and the curve, wherever that happens to be. So for that first bit, this was easy. It was a rectangle. Length times width gave us our area. What if I wanted something like this? What if I wanted I'm going to go over here on the side. What if I wanted the displacement from 5 to 8 seconds? Well, if I look at what's happening from 5 seconds to 8 seconds, that's this chunk here and this chunk here. What is that shape? It's kind of a weird shape, made up of two other shapes. I've got a rectangle down here, and above it, what do I have? Triangle. Well, if I don't look at this as one big shape, I look at it as a composite shape made up of a rectangle and a triangle. This all of a sudden becomes totally doable. And the bell's going to go in like a minute and a half, and so I'm not going to do it today. This is where we end. You have no homework from me today. Your only homework is, if you didn't finish what I assigned yesterday, take a look at that. You'll finish with this stuff tomorrow. Yes, absolutely. I've recorded this. If you need to go back and review it, and we'll finish it up tomorrow. Have a great day.